Okay, hello everybody. So let f be this function. I guess this is from R2 to R. And let A be this set. It's a subset of R2. Compute the integral exactly. Okay, so first let's just draw this set so we make sure we understand what it is. It goes from, so the y variable, the second dimension goes from -2 to 2. That's what this means. And the first dimension goes from 1 to 3. So here's 1, 2, 3. So it looks like this. This is a rectangle. Okay, so that's A. And now, at each point here, so for example, like 1, 1 there, that gets sent to, by the function f, gets sent to x squared, y squared. So that's 1 squared times 1 squared, which is actually the number 1, okay? And in comparison, this point, this is the point 2, 1. Oops. Okay, so then it doesn't get sent to 1. It gets sent to x squared times y squared, which is 4. And this point, which is 2, 0, gets sent to 2 squared times 0 squared, which is 0. And so, everywhere here, there's some value of this function, and we need to somehow compute their weighted sum by volume. In other words, this integral. And the key word here is exactly. We want to get the exact number. Okay, so we can't just break this into a few pieces and do numerical integration. We need exact. Okay, so the fundamental theorem of calculus only works in one dimension. So we need to slice. I'll just use this word sort of intuitively. We're going to slice in one dimension. We could do it that way, or we could do it that way. Let's do it vertically. And compute two one-dimensional integrals in order to compute this single two-dimensional integral. Okay, so how do we do this? Well, let's first fix x. And then when we're fixing x, we need to integrate in the y dimension. Okay, and so this becomes a picture, and I'll just redraw this picture down here with less detail. Here's our region A, and what we're going to do is we're going to fix x at some value, and we're going to allow y to vary up and down. And we're going to integrate in the y dimension. And so this will not give the final answer. It'll only give the weighted sum of the function values on this single line, this line segment where y is moving. So that will not be the final answer, but it'll be a start. So let's see the formulas. In formulas, we'll say, okay, we're going to go from, y is 2 at the bottom, and y is -2 at the bottom, and 2 at the top. So we're going to go from y equals -2 to y equals 2. And what function? Well, we have to integrate a function that sends y to what number? Well, x squared, y squared. If we fix x, then we can view this, x is just some constant, like maybe x is 2. And we fix x at 2, and then we slice there. Then x is a constant, and we just have a function of one variable, namely y. And then so we're going to integrate with that y dimension. So here's our function. And I don't know, let's call it little g. Okay, and we're going to integrate it from -2 to 2. Great, so what does the fundamental theorem of calculus say? So the fundamental theorem of calculus says, well, the integral of g is from, let's say from a to b, is capital G of b minus capital G of a, where capital G is some function we have to find. And in this case, capital G of y will be, well, y squared. So just like partial derivatives, we already knew how to do it. Just fix the other variable. Well, the integral of y squared is y to the third over 3. The x squared just hangs out because it's a constant. It is fixed. Fix x. Okay, great. Well then g of 2, we can just do this. We just do the subtraction. G of 2 is, well, I guess 8/3 times x squared, whatever that fixed value of x is. Maybe we fixed it at x equals 2. Maybe we just fixed it at x equals spooky, mysterious x. Okay, and now g of, what's down here is negative 2. G of negative 2 is, I think, negative 8/3 x squared. Okay, so g of 2 minus g of negative 2. We're just applying the fundamental theorem of calculus to magically exactly compute an integral. It'll be this minus this, which is 16/3 x squared. Okay, so if we fix a value of x, then this is the answer. And we were able to compute that answer exactly by using the fundamental theorem of calculus, integrating only in the one y dimension. Well, okay, what do we do next? Go back to words. Now, let x vary. Integrate over the x dimension. Okay, so in a picture, let's actually, so I would, well, you don't have the luxury of copying, so I shouldn't be allowed to. Let's take this a, and remember we had fixed x before, and we had computed the weighted sum along this thing. And now we'll just let x vary, and we're going to integrate an x from, well, this was 1 to 3, right? Wasn't it? Yeah, the x dimension went from 1 to 3. Okay, great. So we can do this. Let's get a formula color. Integrate from x equals 1 all the way up to x equals 3. What function now? Well, x goes to, okay, what function? Oh, this one. Okay, so here, this function. Oh, let's call it little h, and then we'll need big H to apply the fundamental theorem. And so what is big H for this? Well, big H of x will be x to the third over 3. Over 3, and then we already had a 3 down there, so this is now a 9, 16. Okay, so I just do h of 3 minus h of 1, and that's my answer. Okay, so h of 3 is 16. So 3 3s and 2 3s will cancel, leaving 1 3 up top. And then I plug h of 1, and I get 16 ninths. Okay, so this is what? 48 minus 16 ninths. And that is the magical exact answer. By applying the fundamental theorem of calculus, not once, but twice, we were able to compute a two-dimensional weighted sum of the function values weighted by volume. In other words, an integral. Okay, and so maybe I'll just say this exactly equals the integral over a of f. In all its glorious limiting value, I don't know what I'm saying here. Anyway, this integral is a limit of all sorts of chopping it up into smaller and smaller pieces, and we were able to exactly get that answer, and that's pretty cool. It's because of the fundamental theorem of calculus in one dimension. Okay. Great. So in order to do this, you need words, pictures, and formulas. So make sure you can do, all three of these pictures were incredibly important. These words were incredibly important. And the formulas here were actually, including this. But, this was one set of formulas, this was another set. And so make sure you understand every piece.